Lesson 3 is about polygons. So first of all, you need to know what a polygon is. A polygon is a simple closed figure formed by 3 or more line segments called the sides. So this example here, since this figure has a curve to it, it's not a polygon. This one has sides that overlap, so it's actually 2 separate polygons, but it's not one polygon. And this one is not closed. All of the sides have to be touching in order for it to be a polygon. Okay, so there's some polygons that you know, and the first one is a 3-sided figure that is closed. That's a polygon is a triangle. What do we call our 4-sided polygon? Since there's multiple things it could be, meaning like a square or a rectangle or a trapezoid, we tend to use quadrilateral because that means that there's 4 sides to it. So that title means all of the ones that we talked about there. 5 sides, it's a pentagon. 6 sides, hexagon. 7 sides, that's one people tend not to know. It is a heptagon. 8 sides, a lot of people know. Like an octopus, that's an octagon. 9 again, that's a trickier one. Oop. Nonagon. And 10 is decagon. Okay? So those are ones that you are expected to know. Okay? If it uses one of those words in a problem, you should know how many sides there are. So in our first example, it says determine whether the figure is a polygon. If it is, classify the polygon. If it's not, explain why. So this one is a polygon. It has no curves to it. It's straight lines. There's no overlap. It's closed. Okay. And if we count, there are 1, 2, 3, 4, 5, 6, 7 sides. So that's a heptagon because there's 7 sides to it. So go ahead and try your got it problems. In A, since there's 6 sides, there's 1, 2, 3, 4, 5, 6, and they all intersect at their endpoints. There's no curves. That means this is a hexagon. This one, there is a large curve here, so this is not a polygon. It asked us if it's not, explain why, and the reason why is because it has a curved side. Not a polygon, there's a curved side to it. Okay? Now, I know this is not our typical thought of a hexagon, so when we talk about polygons, if we want them to be all the exact same side lengths, we call that a regular polygon. So any of these named, if those are like a regular hexagon, that means all 6 sides are the same. A regular pentagon, all 5 sides are the same size. So that's usually we draw that. Mine's not going to be exact, but that's what we have in our head as a regular regular pentagon, if you think that through in your head. Okay. The next part, we're going to go to this worksheet. So we're going to name each polygon, the number of the sides, and we'll go from there then. So the first one is our quadrilateral. That has 4 sides. Okay, so take a second and fill in on all of these, the name, the number of sides. Okay? Okay, you should have all of these filled in. These are all regular polygons, so when we're looking at these, the Pentagon, all 5 sides are the same length. The Hexagon, all 7 sides are the same length. Same with our octagon, nonagon, and decagon. Now, I'm assuming you got to this one, and we're a little lost on this. Okay, there are 12 sides to this. Anything over a decagon, we don't have specific names to it. We call it a 12gon. If there were 16 sides, we'd say a 16gon, and so on, okay? So anything over that 10 sides, there's not a specific name to it. So from there, if we want to be able to find the sum of the interior angles, so one that you already know, if you think about, you have a triangle. Now I know my sides aren't going to be straight, but our triangle we already learned is 180 degrees. When we look at our interior angles, no matter what those angles are, if it's a triangle, it will always add up to be 180. We don't know anything about a quadrilateral though. However, we can break that up into a triangle. So I could draw one diagonal in there, and now I've created that there are 2 triangles. So I have 2 triangles in there. I have my one and my second one. So if this triangle is 180 degrees, and this triangle is 180 degrees, the total angle measures of all of them, because this we know is going to be 90, this would have to be 90 if this is actually a rectangle. This is breaking up a 90, so it's part of the 90, the other part of the 90. Well, that's going to be the same thing here. So it's going to be 180, and there's 2 of them. So 2 times 180 gives me 360 degrees for a quadrilateral. Now, if I just wanted to know one interior angle, what I would do is say, okay, if the whole thing is 360 and there's 4 sides, if I want one of them, I divide by my 4 angles, or my 4 sides here. So 360 divided by 4, that would give me 90 degrees. Now, again, that's only for a regular polygon, meaning all 4 angles are going to be the exact same measure. Okay? If this was not, like maybe our quadrilateral was a trapezoid, all 4 are not the same, that's not a regular polygon, so we couldn't use this method to find just one angle. Okay? So the next one is Pentagon. When you're looking at these, when you're breaking them up, you're going to do diagonals. So notice, I'm not going to go one from here to the next vertex here, because that's already a side. So I'll go from this vertex straight across to this vertex. I can go from this vertex straight across to this vertex, and again, this would be a side, so I'm not going to mark that. So I have 3 triangles I can create here. Well, 3 triangles at 180 each, that's going to be 540 degrees. If I want for just one of those, I know if there's 5 sides, there's 5 angles. So 540 divided by 5, I'm going to get 108 degrees. Okay? So we need to go through this and finish filling out our chart. So I'm going to give you time to do that on your own. Go ahead, do that, and then I will fill mine in while the video is paused and show you the answers then. Okay, so let's go through these. For a hexagon, sum of the interior should be 720 degrees, so 1 would be 120 degrees. And again, you can kind of look at my math here. For the first number, I'm taking the number of triangles times 180. Then once I get my total sum, I divide it by how many sides there are. So heptagon would be 900 degrees, and a rounded answer of 128.6 degrees. An octagon would be 1080 for the sum. For 1, it would be 35. For a nonagon, it would be 1260 for the sum, 140 for just 1, 1440 for the sum, 144 for 1, 1800 for our sum, and 150 for just 1. So the key here then is, as we look at this, trying to figure out, okay, what rule could we have so that if I had a 29gon, how can I figure these numbers out without having to draw in all of my triangles on these and count how many there are? Okay, so what formula do you think we could use to find the interior angle? Okay, I'm not sure whether you got it or not, but if you look at our numbers, we always take our number of sides, n, and it's 2 less because if you think about it, I can't draw to the 2 sides that are right next to it. So I'm going to use n for my number of sides. So I'm going to take my n minus 2, my number of sides minus 2, and then that's my number of triangles. Once I know how many triangles there are, I multiply that by 180 because each triangle has 180 degrees. So that would be our formula for that one. Okay? The other part of the lesson today is talking about the sum of the exterior angles. So if I was thinking through, remember our exterior angles is when one of the lines is extended, so it would be these angles. Well, if you look at how they're extended each time and what their actual measure would be, you would find that if I add all of those up each time, the total sum will every single time be 360 degrees. So this is 360 degrees on that one. Okay? And don't forget, you could figure out what those missing ones are because I know my interior angle here is 108. So that would mean 180, this straight line here, this straight line here, this 180 straight line. If I take away 108 for this, that means each exterior is 72. So that's saying this is 72, 72, 72, 72, 72. Okay, and if you're like, I don't understand why this works, as there's more sides, our interior angle measure is changing. It has to get wider for our shape. So our interior angle here is 90, which means this is going to be 90 as well. So here our interior angle is 108, so our exterior has to be smaller. Again, it goes up, so our exterior has to be smaller. So that's why no matter how many sides there are, our exterior sum will always be that 360 degrees. Okay? Then when we're looking at it, the formula to find one measure, well, if I take 360 and divide it by how many sides there are, that would give me just one. For example, 360 divided by, there's 5 sides on a pentagon, that gives me those exterior angles of 72 degrees on each one. Okay, so this kind of serves for you as how to do each of the problems that you might encounter on your homework. So let's go ahead and look at some of these. You've got it 2A and 2B in your notes. Go ahead and find the sum of the measures of the interior angle of a 13-gon and an 18-gon. So go ahead and try that, and then I'll show you how to do it. So on these problems, remember for each one you take the number of sides, subtract it by 2, and that's how many triangles. So this means on a 13-gon I could draw 11 triangles, 180 degrees each. That gives me 1,980 for the sum of the interior angles. On an 18-gon, 18 minus 2 means I can make 16 triangles at 180 degrees each. That's 2,880 degrees. Okay? So that's the sum. What about just one interior angle? So what is the measure of an interior angle of one of the pentagonal panels in a soccer ball? So we have our pentagon. It's a regular pentagon. I want just one of these. Okay, and again, use that sheet to kind of help you figure this out. Go ahead, try it, and then I'll show you how to do the work. So this problem starts off the same way as the last. A pentagon has 5 sides. So we do 5 minus 2 gives me 3 different triangles that I can create. That's 180 degrees. So that's 540 degrees. Once we know what 540 is our total, if I divide it by the 5 sides, that gives me one of the sides. Okay, one of the angles. I'm sorry, not of the sides. Okay, so it always starts out by, just like on these last ones, knowing how many sides you're starting with. Here it was 13, here it was 18, on a pentagon that's 5. Once you know that, you can figure out how many triangles and go from there with the information you know about triangles. The next question says, identify the polygon given the sum of the interior angle measures. So this one's a little bit different than what we've talked about. Okay, so I know I'm starting with 2,340, and I know it has to equal that n minus 2 times 180, so that I know how many sides, so I can tell what polygon it is. You always name a polygon by how many sides there are. So I don't know what n is, so we'll leave that as a variable. And we'll think through how to solve this. There's 2 different ways you can do this. You could distribute if you want and do 180n minus and then 180 times 2. Or the other way to think it through is to say we're multiplying here, so let me divide. That cancels out my 180. So when I do 2,340 divided by 180, I find that that's 13 is equal to n minus 2. To solve that part, I would add 2 to both sides. That means my number of sides is 15. If I have 15 sides, we don't have a particular name for that. That's just going to be a 15-gon. Okay, a 15-gon. So go ahead, try the next one on your own. See if you can find how many angles there are. Or I'm sorry, yeah, how many angles, which is going to tell you the side or the name of the polygon. So when we look at this one, we start with the sum that they gave us equal to our rule here. I divided by 180 on both sides, added my 2, and got that it was a 30-gon for this one. Okay? The next part has another new vocabulary term. So it says a repetitive pattern of polygons that fit together with no overlap or holes is called a tessellation. A sum of the measures of the angles where the vertices meet in a tessellation is 360 degrees. So that's the important part, is that when they meet, they always have to meet together at a 360 degree angle. I lost my paper clip that's helping it stay focused here. Okay. So when we go and look at this next example. It says determine whether or not a tessellation can be created using only regular hexagon. Explain if not. So it says the measures of each angle in a regular hexagon is 120 degrees. And when we look back at our paper here from before, we knew each one was 120 degrees because we took our sides 6 minus 2, that's our number of triangles, times 180, that's 720. And if I break that up into each of the 6, each interior angle is 120. Okay, so that's where we're getting that. So the sum of the measures of the angles where the vertices meet must be 360. That means each of those 120 degree angles must be able to meet up to be 360. So I have to be able to divide 360 by 120 evenly for this to work. If they don't divide evenly, that means those vertices can't be put together correctly. Okay? So when we're looking at this, if you're thinking it through, what it means, I know my hexagons are a little bit, or my pentagons are a little bit different shape. Ooh. Oh, that's why. It's supposed to be a hexagon. Ignore my drawing. Oh, I'm doing it again. This is why Mrs. Lonely usually plans these things out before she starts doing them. And doesn't just try to draw on a whim because she is not an artist. Okay, so hopefully you can kind of get the point here that they have to be able to meet all together. So right here where they're meeting has to be able to create a 360 degree measurement. If it doesn't equal 360, that means there's going to be some gaps in here. Okay, so by taking 360 and dividing it by 120, I can tell that there were going to be 3 in here that would meet together. And since they meet up exactly with 3, it's going to be able to make a tessellation. Okay? So they have 2 got it's. Determine whether or not the tessellations can be created. Well, these numbers you already know. So go ahead for your pentagon, use your 1 interior angle. For your octagon, use your 1 interior angle that we already knew and see if they can meet up exactly or if there's going to be some gaps and we can't create a tessellation. So go ahead and try that. Okay, so you can see on here, I ended up doing all the work just to show you in case you don't have the paper with you. You take your number of sides, so 5 minus 2 or 8 minus 2 for an octagon. That meant we could create in this one 3 triangles and this one 6 triangles. Each triangle is 180, so this is my total sum of the angles on the inside of my shape. If I want just 1, I divide by how many sides there are to get my 1 interior angle. Once I know the 1 interior angle, I take my 360 and I divide it by that 1 interior angle to see does it work out evenly. And on both of these it doesn't, because 10/3 doesn't come out evenly to a number and 8/3 also doesn't. Since 360 is not evenly divisible by the 2 interior angles that I had found, then no, it is not going to be able to create a tessellation. There's going to be gaps in between. Okay, the last thing, and this isn't in your notes, but just remember for exterior angles, we said the sum is 360. So on a pentagon like this, we talked earlier that if I take 360 divided by that 5, I would get each one of the angle measures here. Same thing with the hexagon, 360 divided by 6 means my exterior angle on a regular polygon is 60 for each. For a 15-gon, my exterior angles for a 15-gon would be 24 degrees each. Okay, you can always practice this and find something like a 20gon. Go ahead and find that on your own, and we can check that later on and see if that would be correct for that one. This has a lot of information in it. If you need help, please make sure you are asking questions.